All right, afternoon, everybody. Thanks for joining in. We have Vinay Sawal from NERSC this week, and he reached out to me a couple weeks ago and was pitching the idea of a talk on InfiniBand. And since I'm a network engineer, I don't know much about InfiniBand, so I thought that that was a good topic. So hopefully everybody else thinks it's a good topic too. So I'll turn it over to Vinay to get us started.
Yeah. Thank you, Jason. Hi, everyone. I'm Vinay Sawal from NERSC, and today, we'll be discussing some, information about InfiniBand, its comparison to Ethernet, and why do we need InfiniBand, what advantages it provides in the HPC networking. First of all, thank you very much, ESNet and Jason, for allowing me to give this talk, and second, for to the audience for joining and spending time with me on this discussion. So let's get started. Okay, so first, very quick introduction. I'm a network engineer in the data center department at NERSC, and as you will know in 5 seconds, for the Doudna supercomputer, I am acting as a deputy L2 CAM for technology integration. My work experience spans from pretty much networking stuff from Bell Labs to Cisco to Dell. And if I'm not working, my hobbies are running, kind of like running from things. Okay, so what are the topics that we are going to discuss? Why InfiniBand? Why InfiniBand is, provides advantages and superior to other existing technologies. How are we going to do the fabrics? How the routing and switching works in the fabrics? What the quality of service looks like? How the congestion acts in fabrics with the their specific HPC traffic patterns, and we'll discuss some of the GPU clusters and storage architectures in this discussion. To provide you some context, as you may have heard or seen, we are launching our next iteration or version of supercomputer. It's called Doudna. It is named after Jennifer Doudna, the Nobel laureate. And earlier this year, Secretary of Energy, Chris Wright, he announced this thing at NERSC. This is a deployment that includes NVIDIA devices and Dell servers. And Doudna specifically, enables the development of a productive workflow environment for the DOE American Science Cloud and Genesis mission. So what that means is there are a variety of traffic patterns that we need to support, which provide or posts a lot of load and a lot of specific stringent requirements on the network. So what is the motivation? As you can see, there HPC cares about performance. And, it isn't like a web traffic where you mainly optimize for big flows. The traffic patterns in HPC is, simulations, MPI collectives, barriers, AI workload, and synchronization makes your workload extremely sensitive to delays. There is a thing in NERSC what we call is time to science. So every microsecond of delay that happens in their simulation, in their training, that causes delay in doing their finishing their science. So tail latencies are very, very important to us. We also need bandwidth, but more than that, we need repeatability when the cluster gets busy. So consistency and determinism is also very important. So InfiniBand exists because the ecosystem wants a fabric that could deliver consistent HPC communication with less messiness in the data path. So why not just Ethernet all the way, right? So there are a few things. Even though the later versions of Ethernet is getting better, as we currently stand, there is an overhead. There is a TCP overhead because every Ethernet or TCP/IP is kind of like a packet-based technology, and it is a best effort with enhancements, right? With a lot of reliability and overhead are handled at the higher layers, right? InfiniBand, on the other hand, it bakes the HPC oriented transport behavior, and the most important part of InfiniBand is the RDMA, which is at the center of how the data moves. So in the TCP/IP, you see that there is a kernel involvement, and then you have a bunch of the buffers are getting copied from the application space to the OS kernel, and then to the NIC, and then it gets put on the wire. Ethernet also has a congestion control uh, a point where it is a software-based congestion control, which is primarily reactive. So all these factors, that's why these factors add latency to the overall workflow, and you will see that the latency, typical latency on the Ethernet side is kind of like an order of a magnitude higher than InfiniBand latency. And it's getting better, but there is still a very big gap that needs to be bridged. So what does an IB fabric look like? InfiniBand, also known as IB. So I'll be using InfiniBand and IB interchangeably. So think of an IB fabric as a system, and it's not just a bunch of pipes, right? What you will see is the endpoints are attached via something known as the channel adapters. So they are like equivalent to NICs in your traditional networking. There are switches, and the switches do the forwarding part. And there is an important piece called subnet manager. So the subnet manager is a centralized controller. It's a centralized control plane which performs most of the control plane functionality. So unlike TCP/IP and traditional networking, which is distributed and we run through a lot of protocols like OSPF, BGP, and so on, Subnet Manager is that central controller which takes care of all that control plane information and lets RDMA do all the data plane. And in addition to the Subnet Manager, there is more of a centralized monitoring infrastructure with InfiniBand Fabric that helps deliver this faster and better performance. But in essence, InfiniBand is a switched fabric where endpoints connect through very high radix switches, similar in spirit of that data center fabric, right? The key conceptual shift is that the network is the system, not just the pipes. And like I said, the subnet manager provides the control plane, addressing, routing, and partition related mapping. So here the separation is important. The performance issues are often a combination of what the subnet manager decides and how the fabric reacts to the traffic at runtime. And just to have a little bit of comparison between the two. So again, this talk is not regarding the actual protocol and how many bits and bytes each of these things mean, but rather more like a practical approach. So what we can do is, we can go over some of these items, and we can do like a simple comparison. They are not meant to be exact one-to-one match, right? So in Ethernet, you have seen there is a MAC which gets burnt into the NIC. So similar to that, in InfiniBand, there is something known as a globally unique identifier. And this globally unique identifier can be thought of as a MAC. It is a 64-bit identifier, and which is assigned to each HCA. Then you have LID, LID, a local identifier, and this can be thought of as an IP address. The only difference here is these IP addresses are very specific to a subnet, and that IP address assignment, the lead assignment, is local and assigned by the subnet manager. Then you also have a global identifier in the event where you need to talk out of the fabric, and then that is kind of like a combination of your subnet prefix and the GUID and bunch of other things. And these things are primarily used for in IP over IB, which we will discuss in a little bit. One more thing to kind of like focus in comparison is the P key. The concept of the P key is very, very similar to that of a VLAN, which we will discuss in a later slide. But the concept is still the same. The P keys are used for traffic isolation, and then depending on the application, you can use them for multi-tenancy and security enforcement and so on. Then you have service levels, which is equivalent to Ethernet quality of service primitives such as class of service and DSCP. So this service level on InfiniBand is kind of like a global, similar to that of a DSCP. Then you have virtual lanes, which are kind of similar to the priority queues. And these virtual lanes are actually hardware queues, which are in HCAs and in the switches. Then we already discussed about the subnet manager, which maps the topology and it performs the centralized work of routing. And in the Ethernet, you have OSPF and BGP and all. But in here, we have a subnet manager. Then from a transport point of view, you will see that you will hear these two most common transports called reliable connection RC, which is kind of equivalent to a connection oriented TCP, and unreliable datagram UD, which is kind of equivalent to an UDP. The congestion control happens in InfiniBand at the link level, and it is more like a hardware function and proactive function as opposed to a reactive way of doing, ECN and PFC. And ultimately, the NIC and HCA are kind of equivalent where they perform the similar hardware functionality. Let me take a pause and see if you have any questions. All right. Okay, so we touched upon RDMA, and I think it's a good time to discuss. RDMA is the technology that drives the low latency piece, and RDMA is kind of like extending the DMA over the network. It means the network path can read from and write to memory on the remote side with a minimal CPU intervention, right? So in practical terms, the advantages that you see is you avoid extra copies and reduce kernel involvement in the critical path, which lowers the latency and frees up CPU cycle. RDMA also encourages efficient communication patterns like one-sided operations and predictable completion behaviors. So when you move from Ethernet to RDMA-centric transport, the performance becomes less about packet handling and overhead and more about queuing and path selection. So that's where you get a bunch of advantages over your traditional Ethernet. InfiniBand, supports a bunch of topologies, fabric topologies. You have the fat tree, which we'll discuss in a moment, but it also supports, traditional things like Dragonfly and 3D torus and Hypercube and so on and so forth. But the king of the hill is this fat tree topology. This fat tree topology can be thought of as like a folded clause that we have seen in the Ethernet world. And the reason why it's called fat tree is as you get higher in the on the levels, then the link or the bandwidth gets bigger and bigger. So in this thing, if the leaves are where all the servers or the workloads are connected, and the higher layers are primarily used for routing traffic. This topology scales much better for HPC traffic pattern. And this is also very conducive to something known as adaptive routing that we will discuss in a moment, because it contains multiple equal cost paths, and then it can help spreading the traffic in the times of heavy load. Okay, so let's spend a little bit of time in understanding how RDMA internals work in conjunction with InfiniBand. So unlike TCP/IP, which uses sockets and they are packet-based system, RDMA primarily is a message-based system, right? So what you see is on each of the side, you will have something known as queue pairs, which provide the context of communication and how you want to operation, how you want to execute the operations, and they link what the application posts to what the network transmits. So you have these queue pairs, which are kind of like socket pairs, but these are actually queue pairs which send and receive the messages. Then you have C queue, which is a completion queue, which will have all the received messages and they get consumed. And then the last part is the MR, also known as memory region. And the memory region is the construct where the applications and the nodes decide what are the regions of memory that they will use for remote access, basically, which will allow the remote computers to communicate with, and the local computer to communicate with, right? So you have R keys and L keys, which are remote keys and local keys, that gets exchanged during the channel establishment, which enables this RDMA. So it contains obviously control plane and data plane. And RDMA is the reason IB performs so well. So instead of pushing bytes the traditional way and letting the CPU kernel mediate, what we get is a memory to memory transfer and a much more direct path. And what it means is, the performance bottlenecks don't show up that much, but they only show up during, very critical cases like, path selection and contention and so on. But from a difference point of view, what you see is you have the control plane and the data plane. So control plane is responsible for all the communication establishment or channel establishment, as we saw earlier, where the QPs, they establish the queue pairs, and then they exchange all the local memory region and the remote memory region and all that. And then once that thing is established, then the data plane comes into play, where all the actual heavy duty work of exchanging messages comes into play. It supports the send and receive and all those different operations. So from a InfiniBand communication model, what you will see is this peering or layer to layer communication, where the applications they do transactions, which amounts to the message passing between the queue pairs at the lower layer. And then further down, then comes into the networking layer, where you can do the lids or the local IDs, do the subnet routing, and then the link layers, and in the hardware, they provide all the flow controls and signaling and so on. So this is kind of different than TCP/IP, and kind of similar also. But in this, what you will see is these messages are exchanged between the peers using the InfiniBand technology. So before we move on, I would like to just go very quickly over two issues that we will face in this stage. So the first one is the head of line blocking congestion. And as you may already be aware, this head of line blocking occurs when queue traffic shared a resource, right? Basically, if they share a queue, and the front of the packet can progress quickly enough for any following packets. So in this case, what will happen is, even if high priority traffic arrives, it can still wait if the queue is blocked. So in this case, as you can see, even though the green packet needs to, or if the blue packet that needs to go to a different queue, because the red packet is was blocking them, it cannot follow through, and it is waiting for the red packet to finish, so that then it can go and get to the egress queue. And this head of line blocking is a primary cause of tail latencies, and we want to avoid that. And what we will see is the concept of the service levels and the virtual lanes in InfiniBand tries to mitigate this head of line blocking. And the second is the incast burst. You may have heard of TCP incast, which is very, very similar. So what happens is, uh, when you have a bunch of senders converge onto one receiver, you will see that the receivers or the switch egress, their queues saturate. And when the queues saturate, what happens is the tail latencies increase, and in the really bad situations, the packets gets dropped, and dropping of packet is very critical, at least in HPC environment, because there is an SLA, or there is a requirement where the packets should not drop, because that will trigger a much more adverse effect on the overall performance or overall function of the underlying job. And the common triggers of this thing, we will discuss in a moment, is collectives. Collectives is a concept where uh, a bunch of synchronizing things like MPIs and collective communication happens, or the metadata gets converged in the storage in the storage nodes. Uh, so the effect of this thing is, as I said, the tail latencies will spike and the throughput will collapse. It's kind of like like a collapse or a cascading effect. So how does IB provide that lossless fabric? IB is generally known as a lossless fabric. And the way the lossless fabric is operated, or it provides, is it provides a credit-based flow control at the link level. So kind of like in the hardware. So unlike TCP/IP, where the flow control is a software construct, and it is more reactive when it sees the congestion. The credit-based flow control is more like a proactive effort done purely in the hardware at the link level. So what happens in this case is every link to link, every two nodes which are connected via the link, they have a understanding of how many credits the receiver will exchange the number of credits with the sender. And only when the receiver says, and the sender will only send that many packets to the receiver, that the amount of credit they have. When the packets are transmitted, the credits are returned, and then the cycle continues. When the sender does not have enough credits, what that means is receiver cannot drain the buffer fast enough. And so instead of doing the tail drops at the receiver, what the sender will do is the sender will throttle the sending, and the sender will not send that fast. But that obviously has tail latencies, increasing of the tail latencies. But what it will do is it will not cause into that the collapse of the whole throughput, because every packet drop will trigger a bunch of additional uh, operations, because this packet is in the context of some job that is happening, and every packet drop will trigger some kind of redoing of, say for example, gradient learning and so on, right? So this is a very important concept where the our objective is, we want to mitigate the packet drops at the expense of a little bit of latency, because packet drop is more detrimental than adding a little bit of latency. So again, the lossless does not mean that there will be no packet drops or there will be no congestion. Lossless in this case means that InfiniBand will try as much as possible to not drop the packet, but the congestion will still be there. So there will be a mitigation effort to get ahead of the congestion. So now let's talk about the routing. And the Like I said, the subnet manager is the central controller for routing. And subnet manager takes care of, it finds all the paths, and it configures the LIDs in each of the HCAs and each of the switch. And subnet manager takes care of all the routing functionality. The Since our objective is performance and repeatability and throughput, generally the deployments are very simple. You would only need so you will see that this is like a one flat network, because that performs the best. Only when you have some very specific requirements, that's when the actual routing in the system works. So similar to Ethernet routing, what you will have is if you have two subnets, then you will have to go, inter subnet routing or inter VLAN or inter PK routing happens via router. But typically, this is a very special case because every hop, entails some additional latency, which is what we are trying to avoid. And from a routing point of view, there are actually two kinds of routing. One is called static routing, and second is an up-down routing. Static routing is what the subnet manager, programs by pathfinding and configuring those things. And up-down routing is kind of like an equivalent of a spanning tree, where similar to spanning tree, what you do is it is designed to prevent loops and deadlocks in the network by restricting the directions that traffic can take. But this is not that big of a problem in InfiniBand networks. So static routing is generally what is used with an adaptive routing functionality, which we will cover in a moment. Okay, so before we go to adaptive routing, one important factor here is the PKey, as we discussed. So PKey is kind of like a VLAN concept. It can logically isolate the traffic, just like VLANs isolate the traffic. And what it does is it can define which nodes can communicate to other nodes. These P keys are enforced in the hardware in HCAs and switches, and they are generally used for, like I said, multi-tenancy, access control, security policy, and so on. So it allows you to isolate these nodes at the network level. Okay, so adaptive routing. So adaptive routing, the concept of that is uh, it's a real-time adaptation of routing paths while the traffic is flowing. And so this is not a static, it's kind of like a dynamic routing based on the load on the network, right? So adaptive routing, changes how traffic chooses among available paths as conditions involved, right? So instead of committing to a single path for all the flows, the fabric can steer traffic to reduce hotspots and distributed route. So as you can see in the example, instead of having a single path and having overloaded and the buffer getting filled up and tail latency is increasing, adaptive routing can find equal cost paths and it can spread the traffic across in real time to mitigate that congestion part, right? So the advantage of that is improved performance in the high traffic networks by avoiding congested links. So you can do better load balancing, as the traffic is distributed more evenly across the available paths. Okay, so then let's move on to IP over IB. So what is this? So this is effectively, the bridge between the Ethernet-based applications and InfiniBand fabric. Most applications today are written for TCP/IP. So instead of rewriting everything for RDMA, IP over IB provides a compatibility layer. It allows TCP/IP applications to run over an InfiniBand fabric, and this is useful operationally because it reduces migration friction for tools like SSH, NFS, control plane, and management workflows. But one should know that IP over IB also has an overhead because we are running closer to the Ethernet-like model, right? But which is not a big problem here because we use IP over IB primarily for control plane applications and management plane applications. So what you will see is it basically injects itself, the TCP/IP stack is injected into the IB fabric, via the different paths. And from a practical deployment point of view, what you will generally see is HCA will have a separate interface. It's kind of like a sub interface for an HCA, and they are like IB0, and they are associated with a P key. So that IB0.8003, what that means is it's an IB0 subinterface 8003, and the IP address is 10.1.2.10. So that enables us to do pure, TCP/IP based communication on the InfiniBand fabric, and that will be very useful when we get to applications like uh, you know the setting up of communication channels between NFS and things like that. Okay, so how does the InfiniBand storage architecture look like? And this is very apt based on the, from the previous slide. So storage architecture, you can have, many different options. It's pretty much, you can decide how you want to do it. For Doudna, what we have is we have a storage, subsystem directly built in the InfiniBand fabric. Uh, and uh, and we also have an external source storage system which is external to Doudna, and we it is like a separate storage fabric in our NERSC outside of the Doudna system. So you can pretty much have GPFS, NFS, Lustre file systems, and you can simultaneously communicate using either the native RDMA constructs or IP or IB between these two. For example, when so our storage nodes, what you see here is they are all vast data nodes, and yeah, what we plan to do is we use NFS v3 as our home and home file system mounting on the compute nodes. So these storage nodes, they use NFS, which is primarily a TCP/IP based mechanism. And the beauty of this is the control of the communication setup, all the setup happens at IP over IB. And once everything is exchanged, then the data plane happens over RDMA. So you have RPC over RDMA for the data plane and IP over IB for the control plane. And this is how we achieve the performance and utilize the InfiniBand fabric. GPFS, we have a GPFS fabric outside of Doudna in the NERSC data center, and we communicate through all the GPFS via that Ethernet to IB gateway. So again, that is all IP-based communication. So we have an IP over IB interface on the compute node, and that is communicating to the GPFS servers outside of the Doudna supercomputer using the NERSC data center. Let me pause again and see if we have any questions.
And then I've seen so far.
Okay, thank you. Moving on. All right. So, what is the driving force behind all this InfiniBand and everything else? So the primarily what we see is MPI and the collective communications. These are the two middleware libraries that drives pretty much all HPC traffic. And primarily the collective communication puts even more load because there are some underlying requirements. So say for example, all reduce, you may be familiar with this concept of all reduce in the collectives. What it does is, let's say if there is a big job that is running on hundreds of GPUs. So what happens generally is if you have a data set and during the training phase, if you have a data set, that data set is divided up into mini batch, and parts of the data is given to all the GPUs, and then the GPUs are calculating or they are computing their gradients. Now, these gradients need to be exchanged to all the other GPUs so that they can get on to the next one. So that concept is the all reduce, where aggregation data from all members are sending the results to one member or all members, right? So in these patterns, what happens is this is kind of different than your traditional TCP/IP traffic or web traffic. What happens is this traffic pattern has a very low entropy. And what that means is when these hundreds of GPUs, they start doing generating their calculating their gradient. So they start, it's very synchronized. So they start at one point t equal to 0, and they all finish approximately at the same time t equal to n.
So we do have a
Yeah.
question that just came in. Um, Does IB or IP over IB apply equally to IPv4 and IPv6?
Yes, that is correct. IP over IB is a concept that can perform on V4 and V6, and you can assign similar to any NIC, you can assign IPv4 addresses and IPv6 addresses to that interface.
Thank you.
Okay, so back to the collective communication. So because of this low entropy traffic, the fabric does not have a whole lot of wiggle room because all this all this data is coming at the same time, right? So that is why it's very, very important for us to have a system, a fabric where there are no packet drops, the tail latency is very, very low, and the performance is very, very high. Because this is the reason why I was telling you about is if you have packet drops, then those packets effectively are, some information about the gradients. And if the gradient information is lost, then the CPU will have to do some mitigation or do some redoing some of the calculations and then restarting the whole process. That's why having a performance and tail latencies are very, very important to us. And similar to that, there are other concepts called reduce scatter, where aggregating the data from all members and scattering the results to all of them. Then there's a broadcast where sending the data from one member to the all of them, and then all gather is collecting different parts of the data and distributing among all members. Okay, so that brings us to what are the different flows that we will that we encounter in HPC and specifically in Doudna. So primarily what you will see is one, you will have the, inside the InfiniBand flows, like for example, compute to compute communication or compute to storage. And this primarily, the pattern is for the MPI jobs and the nickel jobs. Nickel is the NVIDIA collective communications library, which is what the collective communications will do. Then you have the traffic flowing from inside the fabric to say GPFS or some other file systems. And then you have, there could be some real-time streaming traffic that is coming from the instruments directly to the compute nodes, and then some, user login and some filers and all that. So we need to accommodate for all the different kinds of traffic patterns while, keeping the performance and while keeping all the throughput. So then, let's look at what is the typical job workflow in an HPC, right? So the first is some scheduler, Slurm in this case, it starts, scheduler places a task across multiple nodes. Now this job could span across hundreds of nodes for big simulations or big AI training, right? And this is where the distribution begins. Then in the step two, what you will see is, so the picture kind of shows the underlay and the overlay. So the bottom part is kind of like the physical deployment, and the top part is the overlay of how the logically things happen. So in step two, what you see is the connection establishment. So before the data moves, the endpoints establish queue pairs, and this is kind of like the connection, IB's connection model. Then in the step three, the communication actually begins. So for MPI, there will be a lot of small messages, and for the collective communication library, you will see a large collective transfers. Then during this process, the actual fabric gets involved, right? The traffic enters the fabric, and then as we discussed, we do adaptive routing because we have multiple paths. And then the adaptive routing decides where the packets go, right? What will also happen here is the quality of service. We will do a congestion control and the quality of service. And this is where this is the place where we take care of the incast bursts of or head of line blocking and the quality of service prioritization. And once the job finishes, what you will see is the best performance, best throughput. It's on the same hardware, same job, but the performance depends on how the fabric is behaving and how we configure it. So that brings us to how do we do this costs or quality of service? And this quality of service can be thought of as hierarchical, because at the lowest level what we want to do is we want to make sure that we do the physical isolation, or rails as they call it. So basically the traffic is isolated between the physical NICs, and so you have dedicated NICs for dedicated kind of traffic, so same for the nodes and for the gateway. Then moving on to the next level, then what you can do is you can do logical isolation. And the biological isolation, what I mean is, let me quickly go over the next picture like this. And what you will see is logical isolation means you will have the service levels, which are the global quality of service constructs. They will be mapped into the physical constructs called the virtual lanes, and that can provide you the logical isolation. Then and this will be logical isolation at the fabric level versus the gateway level, because you can actually provide that isolation by doing the mapping between the Ethernet side of quality of service primitives to the InfiniBand side of quality of service primitives. Basically DSCP versus SL mapping. And then on top of that, you can also have an application layer of quality of service, where you can have a job-based quality of service in the InfiniBand, or you can have real-time services by changing the DSCP values, or you can have Rocky functionality, which is also kind of like a real-time, also a quality of service specific using PFC and ETH and all that, ETC, right? So how do we want to do this traffic classification then, right? We know that there are all the different kinds of traffics, and this is basically first among equal problem, right? I mean, everything is important, but some things are more important than the other. So what we can do is we can define traffic classes. All the critical RDMA traffic can be assigned one service level, and then you can go down in the priority. So, the most critical items like GPU to GPU communication, which uses this middlewares and nickel and MPI, that can be given highest priority. Then you have all the storage traffic that can be given medium priority. And then you have the IP traffic. Because IP traffic is controlled traffic, you can give them the lowest priority, uh, ensuring that we have enough bandwidth in our system. And as I mentioned earlier, we have plenty of bandwidth for the InfiniBand. And as I will, each of those HCAs are XDR HCAs, 800 gigs HCAs. So every node on the InfiniBand fabric will have 1.6 terabits. Right? So if we want to see the traffic paths, how these traffic paths are going to go, what we will see is we can have this mapping table, where at the HCA side we can select that the highest traffic will go on VL0, and the medium and lower traffic can go on VL1. And the reason for that is this mapping will dictate how we avoid head of line blocking. So as you can see, if SL0 is the highest traffic, there is nobody to block it. You will not run into that head of line blocking problem here. For the other traffic, which are not very sensitive to latency and thing, they can incur a little bit of head of line blocking, and that is okay, because that's what our priorities are. Questions?
None right now.
Okay, right. So finally, what we see is, this is kind of like the whole Doudna architecture looks like. We have, as I was just saying, we have very distinct networks in this architecture. We have the InfiniBand fabric, which is the engine that drives the performance and the throughput. Then we also have an high-speed Ethernet traffic, which will provide all the supporting roles for all the management nodes and all the different data exchanges and all the workflows and jobs. Then we have a cluster management network, which can be thought of as an out-of-band network, which will be used to manage this whole infrastructure. So this management network is kind of like air-gapped. Only the administrators have access to it. Then you have some isolated air-gapped network storage networks. See, for example, in the Doudna architecture, what we have is we have VAST is our storage of choice, and all those vast C nodes and E nodes, they are connected via a backend network, which is an air gap network, which is not exposed to anything else. And all the storage work functions that needs to be done of replication and synchronization and all that happens in that backend network. So uh, in this particular case, right, what we see is, coming to the conclusion. So InfiniBand is not just a faster version of Ethernet, right? It's a different model built around RDMA, which enables low latency, high efficiency data movement, and provides superior performance. The fabric, along with the mechanisms like routing and congestion control and quality of service, it ensures that the performance remains predictable even at the large scale. And in the real deployment, you have diverse workloads like MPI and GPU training and storage that share all the same network, making uh, a good design very essential. In this case, simple is beautiful. We don't want to add any more complications because simple is better. So so if there is one takeaway, it is this. RDMA drives performance and the fabric enables the scale, and the thoughtful design ensures consistency. And as we discussed earlier, this is not a question of InfiniBand or Ethernet, right? So if somebody were to ask you, what do you want to choose, InfiniBand or Ethernet for your HPC? The answer is yes, right? So we need to pick both of them because one is not better than the other. They have their own use cases, and they have their own pros and cons, and they are used for different things at different places. Okay, so with that, this is kind of like the whole presentation. I'm sure I have skimmed over some of the concepts because to accommodate all these things in a given amount of time. If there is enough interest, we can do a deeper dive at a later stage. But at this point, I would like to open it for questions that you may have. Yeah, please go ahead.
All right, thank you so much for going through that. So James has a question. You should be unmuted, James, if you want to ask it.
Yep. So what sort of scale would you run InfiniBand at? Would you keep it restricted to a single cluster? Would you have a single InfiniBand fabric that would serve multiple clusters in the same facility? Is there even an option to like run InfiniBand over, potentially two different buildings, things like that? What is the sweet spot for InfiniBand?
Excellent question. InfiniBand can be deployed over multiple buildings. In our case, and I will get to it in a moment. In our case, we have a one floor of data center, and within 100 meters, we have the whole deployment of thousands of nodes in hundreds of racks, all deployed in a single InfiniBand fabric. You can have one single fabric and you can logically basically divvy up it into multiple different subnets. But as I was saying, in order for those different subnets to talk to each other, then you will need a routing functionality, which will add more complications and more latencies and hops. So simplicity here is the key. What you
Mhm.
want to do is, depending on, first you need to identify what your traffic patterns are, what your latency requirement is, what your throughput requirements are, and then you want to design your InfiniBand fabric. In theory, you can deploy up till about 48,000 nodes in one single InfiniBand fabric, which is, quite a lot, even though there is a theoretical limit. And as we are getting to bigger and bigger, 70 billion parameters of training for all these large language models, we sooner or later we will run into that thing. In which case you can deploy multiple different fabrics and you can connect those different fabrics via routing functionality.
Gotcha. So is it typical to have a single fabric like just a homogeneous node, like where you don't have many different types of nodes? You might have like one or two kinds of nodes in an InfiniBand fabric.
Yes, so primarily what you will have is you will have like main three kinds of nodes.
Mhm.
One is a compute node, and that compute node will serve the purpose of doing the computation. And generally, what you will see is that compute node, may have one CPU and two GPU, or you can have an NVL4 where you have two CPUs and four GPUs connected together. But there you will have to worry about the NUMA domain and all that. But I mean, that gets complicated.
Yeah.
So you have a compute GPU, I mean compute node. Then the second variety could be a storage node where the purpose is to provide storage functionality. So it is optimized for storage and you have like a bunch of NVMe drives and so on and so forth. And then the third type of node could be a management node. So in our deployment, like I was showing you, uh, here you will see that on the far left you will see this management node, and this management node we also call it workflow enablement node, and these are the login nodes, and these are all the nodes where people will deploy their containers because we have a container services running there which is called spin. So we will have like a bunch of, bring your own container, you can have Jupyter deployed there. So this type of nodes are primarily for the user to deploy their workloads or deploy their jobs,
Okay.
right? So these are the main three kinds of nodes in a typical InfiniBand fabric. You can, however, divide these things into, logical partitions using P keys. You can have all the storage nodes in one P key and compute nodes in other P key and so on and so forth. But like I said, again, in order for them to communicate now across the P key, then you need a little bit more of communication pattern, which really you want to avoid, because if you think about it, that InfiniBand fabric is kind of like a isolated fabric.
Yeah, that makes sense. All the
All right.
first so Michael can ask a question before we run out of time.
Go ahead,
Okay.
Michael.
Okay, thanks. I may just be thinking about it from a traditional IP networking perspective, but something I'm not clear on is whether InfiniBand is intrinsically a packet-based network or a streaming network.
Okay, so at the lowest level, InfiniBand, I mean, obviously you will have to have the packets that are flowing, right? But from a construct point of view, right? So from a construct point of view, I mean, ultimately you will have at the link layer, you will have packets flowing, between the two nodes. And
Okay.
but at the higher level, they are more like messages which are exchanged between the memory regions, which are dictated by the applications.
So they are, so it's packet-based, but not necessarily fixed size frames like you have in Ethernet.
Ethernet has a very fixed size frame. So again, it depends on what you want to do, like, right? And I think we covered this. So there are two kinds of transports, or there are actually four kinds of transport.
Yes.
But the most common types of transports are reliable RD is, I think, what is that? Reliable
Yeah.
data connection, right? Reliable connection, which are like TCP. And in here, you can have a 64K of the packet size. And in your unreliable datagram, which is most commonly used, you will have a MTU of 4K, right? So 4,000 bytes of InfiniBand packet,
I
right?
got it.
Right. So it all depends on how you want to configure it, what your scale is, what is your scope and what your requirements are. I can tell you that we plan to use this UD, unreliable datagram, because our scale is very, very large. Thousands and thousands of GPUs, performing all this kind of work. So we have, unreliable datagram as our transport of choice.
Okay, thank you.
Cindy, if you want to go.
Sure. Thanks. This has been a really good presentation. We are mostly using Ethernet now, but I can see that we're going to have to make a transition over to InfiniBand. So can you highlight more the Ethernet InfiniBand gateway? Because I think we're probably going to have to run them both in parallel for some time as we make that transition. But can you talk about that and how it adds, I'm sure it adds some kind of latency to the transfer?
Yes. So this InfiniBand gateway, I'm happy to share, is the actual device is called a Skyway, which is an appliance-based device, produced by NVIDIA, right? And what it does is, at the lowest level, it is basically a translator. It will translate the Ethernet packets into InfiniBand packets, right? It's that simple. Uh, Depending on how you configure these things, it may add a little, I mean, the translation will take time and it may add a little bit of latency. But if you are worried about, say, because GPFS is kind of like a very latency sensitive, protocol, what we have seen so far is we have not seen any major issue with latency, if because the way we have designed this system is we have dedicated rails connected for this gateway between the InfiniBand fabric and the Ethernet fabric, right? So what you will see is we have 12.8 terabits per second of throughput between the InfiniBand fabric going out to our data center, and that is throughput enough that there will be no latency involved between our GPFS servers, which are in a separate fabric, and the GPFS clients, which will be running on the compute nodes. Did that answer your question?
It does. Thank you.
Yeah, thanks.
All right. Well, we are at time, so I'm going to need to end it because I need to get to my next call. But thank you again, Vinay, for going through all of that. Really helpful. If you can send me a copy of the slides, I'll make sure that those get posted with the recording from today.
I will.
And go ahead.
Yeah, I will definitely send you a copy of that thing. And once you have the recording up, if you could be so kind to please share the recording, because some people who were unable to join would like to see that.
Yep, absolutely. And for those that are still listening, we have a late ad for next week. Steve Wallace from Internet 2 is going to come on and talk about the local preference probe work that he's been doing with Internet 2. So I will send out an announcement about that as well, and hope everybody has a good weekend.
Yep. Thank you very much. Thank you all for joining. Bye.
Thank you. It was great.